I should start by thanking Jyotishman, the colloquium coordinator, for allowing us to merge the MLM lecture with our usual institute colloquium. So welcome to both the institute colloquium as well as the 13th Madan Lal Mehta Memorial Lecture. I'm going to start proceedings by telling you a little bit about the MLM, Madan Lal Mehta MLM lecture series. This lecture series was started in the year 2010 and was initiated by a generous endowment given to us by Mrs. Rani Mehta, the late Madan Lal Mehta's wife. Mrs. Mehta gave us this endowment and urged us to use the money to invite extremely eminent lecturers from around the world to come and address us on topics of excitement and current research excitement. We've been trying to do that. We've had one MLM lecture every year starting with 2010. And then the last year, as part of the 75th year celebrations of the 75 years of TIFR, we decided to have multiple MLM lectures. So these lectures have been, as I said, given by extremely eminent lecturers. Just to give you a flavor for that, the last 5 MLM lecturers have been Professor David Kaplan, that was in 2017, Professor Ashwin Vishwanath, Bert's colleague at Harvard, in 2018, Professor Ashok Sen, the great Indian string theorist, in 2019, Professor Wendy Friedman in 2020, and earlier this year we had Professor Edward Witten. Today's lecturer, Bert Halperin, continues this. Continues in this tradition of eminence. Perhaps the next MLM lecture is also tentatively fixed up for later this year. That will be delivered by Professor Savas Dimopoulos from Stanford University. Perhaps I can tell you a little bit about ML Mehta, Professor Madan Lal Mehta, in whose memory we're having this lecture series. Professor Mehta was born on the 24th of December in 1932 in a small village in Rajasthan near the town of Udaipur. He did his MSc from the University of Rajasthan in Jaipur, getting his degree in 1956. Then he came and spent 2 years in the Tata Institute of Fundamental Research between 1956 and 1958. TIFR at that time, for those of you who don't know it, was a young institute bubbling with excitement, and was a developing institute. And one of the ways that our first director, Homi Bhabha, and his colleagues who set up the institute encouraged the growth of science in TIFR and in India was to identify brilliant young students and have them sent abroad to complete their PhDs. ML Mehta was one of these brilliant students in this tradition. He went abroad to France and did his PhD with Professor Claude Bloch, working on the physics of materials at low densities, receiving his PhD in 1961. From 1962 to 1963, Professor Mehta worked at the Institute for Advanced Study in Princeton. He then returned to India and worked in Delhi University for a few years before returning back to the US in 1966, where he went to work at Princeton and the Argonne National Laboratory. In 1967, he finally moved back to France, to Saclay, where he spent the rest of his career. After his retirement in 2005, Madan Lal Mehta came back to India in January 2005, and finally passed away on the 10th of December in 2006 in Udaipur. Okay, Madan Lal Mehta was a great mathematical physicist, and his accomplishments include the development of the orthogonal polynomial method for the study of random matrices, as well as many detailed studies of circular ensembles in collaboration with Freeman Dyson. But for many of us who grew up were trying to learn about random matrices and matrix ensembles, many of us who grew up trying to learn this are most familiar with Madan Lal Mehta from his classic textbook on random matrices, which many of us have read from end to end and really enjoyed reading. It's a fantastic book, and just, because from the pleasure I've taken in reading that book, I'm really honored to be introducing Madan Lal Mehta. Okay, so that's it from my end. One or two organizational comments before we start. The next thing that will happen in the series of events is that Kedar will introduce Professor Halperin. Then Professor Halperin will take it from there and present his lecture. At the end of the lecture, Professor Halperin has kindly agreed to take questions. We request all of you to save your questions for the end of the lecture. You can ask your questions by raising your hand if you're on Zoom, or typing your questions into the chat box on Zoom or the discussion area on YouTube. Urgent questions can be typed into the chat box and discussion area even during the lecture, but we will try not to disturb Professor Halperin. And some of the students who are helping out with the lecture, with this procedure, might try to answer some of these clarificatory questions. More detailed questions we'll keep to the end to be addressed by Professor Halperin. Okay, so with that, let me hand over to Kedar for an introduction of Professor Halperin.
Okay. Good morning, afternoon, evening to all of you. This is Kedar Damle of the TIFR. It is my pleasant duty today to introduce the speaker, Professor Bert Halperin of Harvard University, who has accepted our invitation to deliver this 13th Madan Lal Mehta lecture. Professor Halperin completed his early education in New York's public school system and went to Harvard for his undergraduate degree. After Harvard, he chose to take up graduate studies at Berkeley. The choice of Berkeley, I think, being motivated at least in part by better weather compared to Boston. At Berkeley, he started working on a thesis problem with John Hopfield, in which he was motivated by some questions from polaron physics to analyze the quantum mechanical behavior of a particle in a random potential in one dimension. Midway through his thesis, he followed his advisor back to Princeton and bad weather, but his thesis work led him a little later to a theory for the low energy tail in the spectrum of such a particle. Such tails are, of course, now called Lifshitz tails in recognition of related work by Lifshitz in the former Soviet Union. After a brief postdoctoral stint in Paris, he started a decade-long stint as a member of the technical staff at Bell Laboratories. It was during this period that he collaborated with Pierre Hohenberg to develop their celebrated and comprehensive theory for dynamic critical phenomena. And the remainder of his career has been spent at Harvard, where he is now the Hollis Professor Emeritus of Mathematics and Natural Philosophy. And the mathematics is spelled with a C and a K, and I'm told Bert had a hand in making sure it stays that way. Early in his tenure at Harvard, he was motivated by closely related work of Kostelis and Thouless to develop with David Nelson a theory for dislocation-mediated melting of two-dimensional solids with triangular symmetry. And this led to their celebrated prediction of the hexatic phase in two dimensions. In unrelated developments, soon after, the integer quantum Hall effect was discovered. And in response to this discovery, and I think motivated by some arguments of Laughlin, Bert developed a theory for the quantized Hall response in terms of one-dimensional states at the edge of the sample, which carry electrons only in one direction, and in doing so evade and avoid being localized by disorder in the sample. This theory, which relates a quantized response to a topologically protected property of the edge, has become really the prototype for our more recent understanding and excitement about topological insulators. A decade or so later, he went back to the quantum Hall effect and played a rather crucial role in developing a theory for the unquantized response at filling fraction half in such samples. In recent years, he has shifted his focus to the study of quantum behavior of electrons in extremely confined geometries. Over his long career, he has mentored a large number of students and postdoctoral fellows, and many other physicists credit his sage advice as being crucial to their own work. Many of his former students, Daniel Fisher, the late Chris Henley, Catherine Callan, to name a few, are well known to this audience as distinguished physicists in their own right. His contributions to our subject have been recognized with numerous awards and honors, including the Buckley Prize, the Onsager Prize, the APS Medal for Exceptional Achievement in Research, and the Wolf Prize in Physics. Today, he will talk to us about fractional charge and statistics in fractional quantum Hall states. And with that, Over to you, Bert.
Okay, well, thank you very much. Can everybody hear me? This is really quite an honor for me to be giving these lectures, partly because of the very distinguished predecessors that you've mentioned, and of course, like most physicists, or certainly in condensed matter, we know, and I guess really also in string theory, we know very well Mehta's book on random matrix theory, and we've used it in one way or another to understand the beautiful properties of random matrices. What I'm going to be talking about today is a bit different. It is about the quantum Hall effect, and let me see if I can share my screen properly here. Whoops, wait a minute. Now let's see. Why is that not working? Let's see, let's try it once more. Let's go back here. Sorry about this. Okay, I think we're in the right place now. Great. Okay, let me just get rid of one more thing here. Fine. Okay, so what I want to, the title of my talk is Fractional Charge and Fractional Statistics in Quantized Hall Systems. Whoops, wait a minute. Now that's a problem. Whoops. Okay, and just to remind you what we're talking about here, so fractional quantum Hall states are strongly correlated states that exhibit some very remarkable properties, among which is that they host quasi-particles, elementary excitations that have fractional charge, fraction of an electron, and they have something that we call fractional statistics, or in some cases something even more exotic but related, called non-abelian statistics. And my talk will review these concepts and discuss the status of experiments to try to exhibit these properties, to try to see them directly. So just to remind you what quantum Hall effects in general are, it refers to a very large set of peculiar phenomena in two-dimensional electron systems, typically taking place at low temperatures in strong magnetic fields, of which the most dramatic effects are the ones called the integer and fractional quantized Hall effects. And those are the ones I'll be talking about today, especially the fractional quantized Hall effect. But there are many other interesting things, including the unquantized quantum Hall effect, which Kedar mentioned. There's Wigner crystallization, formation of stripes, and so forth. And these have been studied in a variety of materials. The original ones were in, for a long time, they were primarily studied in electrons in semiconductor structures, such as, for example, I think the most extensively, electrons trapped in a very thin layer of gallium arsenide surrounded by aluminum gallium arsenide, which acts as a barrier to confine the electrons in this layer. But they've also been studied in many other systems, in particular graphene, since it's been discovered, has been a focus of much of this work, and other systems as well. And again, let me just remind you what the general features are. The starting point is to think about the Hall geometry, where we have a sample in the plane of the the picture here, and let's get the laser pointer up. So we want to run a current through in the x direction. We attach leads on the two sides we measure that just measure voltage without drawing any current. So we measure Vx and the perpendicular voltage Vy. We define the Hall resistance Vy over Ix. The longitudinal resistance Rxx is Vx over Ix, and those can be measured. And what happens in the quantized Hall state is that you see a plateau in the Hall resistance. There's a finite range of magnetic fields or electron density, both, of which the Hall resistance is absolutely a constant, and it obeys a very remarkable law that the Hall resistance is 1 over quantity nu times h over e squared. H is Planck's constant, e is the electric charge, and nu is either an integer in the integer quantized Hall effect or some simple rational fraction, usually with odd denominators, but occasionally with even. And once you get one of these plateaus, this is can be extremely accurate to as much as a part in 10 to the 9th has been shown. It's independent of the precise shape of the sample, of what material it's made of. Once you get into the plateau, at the same region, when you're in one of these Hall plateaus, the longitudinal resistance vanishes, or it's small, unmeasurably small. And as far as we know, we believe that these results are actually exact in the limit of temperature going to 0, or for a large sample. Of course, in a finite sample, they're not exact, but they can be extremely accurate, as I've said. And if you invert this resistivity tensor, what you find is that means that the electrical conductivity tensor should obey the longitudinal part is 0, and the Hall part is nu. Inverting the Hall resistance, it's nu times e squared over h. And again, the current is perpendicular to the electric field, and so therefore both the diagonal part of the resistance and the conductivity vanish. And this is a classic picture that you've probably mostly seen from that dates back to 1987 of showing these are the red curve, just concentrate on that. That's the Hall resistance, and you see these plateaus, and they're labeled for the value of nu. So these are integer plateaus here, 1, 2, 3. And here you see fractions at 4/5, 2/3, 3/5, 5/7, 5/9. Not all odd denominator fractions, but many of them are here. And nothing is happening at nu equals 1/2. We now understand what the basic conditions are for finding a quantized Hall effect, integer or fraction. What you must have is a sample that in the bulk, far from edges, if you have an ideal sample with no impurities, the system should have an energy gap for creation of any kind of mobile charges. Now, in the presence of impurities, you don't usually have an actual energy gap, but there are usually localized states in the gap where electrons may be bound to impurities, for example, with energies in the gap. But the point is they're localized, and these carriers, this is very important. There are these localized states often, but the carriers on them freeze out into the localized states at low temperatures, so they do not contribute to the electrical conduction, and they can, but they can be still important as acting as a reservoir, so that you can vary the density, for example, of magnetic field, and only localize. The only thing that changes is the number of electrons or particles in localized states. So the bulk in this case is essentially an insulator, because there's no mobile carriers at the Fermi levels. Current cannot flow in the direction parallel to any applied electric field. On the other hand, because there's a magnetic field present, current can flow actually in direction perpendicular to the electric field, which doesn't do any work. And it's carried by electrons that are well below the Fermi surface. And that's what can give rise to a Hall conductivity. Now, a real system is not infinite. Of course, it also has edges. And it turns out that in a quantized Hall state, if you have a non-zero Hall conductance, the energy gap must vanish along the sample edges. These are the edge states that Kedar mentioned. And they form a peculiar type of one-dimensional metal. We call it a chiral metal, because at least over large length scales, carriers travel only in one direction along each edge. They're, of course, opposite on the two edges. And if you have a ribbon-shaped sample, let's say it's very long in this direction and finite in this direction, you can set it up in such a way, because there's no conductivity in between, you can have different chemical potentials on the two edges, and it'll last for a very long time. And in that situation, I declare there will actually be a net edge current, which will be, because you have different chemical potentials on the two edges, you have different occupations, you have more electrons, say, in this edge than in this edge, you'll have a net current in one direction or the other. And of course, the total current along the ribbon will be the sum of the edge current and the current in the bulk, which can also exist. So that's the total current, and also the total voltage difference that you would measure if you connect the voltmeter on either of the edges or between the two edges, it will be the sum of the electrostatic potential difference that we're usually used to, plus the chemical potential. A voltmeter measures the sum of these two things. And so the measured Hall resistance, RH, is the ratio of this total voltage divided by the total current. And that's what is constant. The individual parts may vary, but the total must be constant because of basically charge conservation. If you have current flowing along the ribbon and the characteristics of it vary slightly from one place to another, the current can't change, so the resistance, as long as sigma xx and sigma yy are zero in the bulk, you have no current across, and this remains a constant. And that's why really the Hall conductance is so accurate. Okay, so the question is, how do we get energy gaps? So in the integer case, and we want it, of course, with nu not equal to zero, you can always have a pure insulator. Then for the integer case, it's relatively simple because we know that for non-interacting electrons in 2 dimensions in a magnetic field, you have discrete energy levels, which are called Landau levels, and they're separated by the cyclotron frequency. Or if you have 2 spin states, you have a Zeeman energy separating them. So there's an energy gap between them. Because there are a discrete number of states, but there's a very large number of states, the discrete number of energies, but a very large number of states in each energy level. In particular, there's 1 electron per flux quantum of magnetic field. And so at the Fermi level is between 2 Landau levels. So the energy gap is then in a filled, there's an energy gap between the filled states and the empty states, which are in a higher Landau level. But then the filling fraction is an integer. We define F as the filling fraction, it's a very important number. It's the ratio between the number of electrons to the number of flux quanta. And now if we have, we'll have an integer number of Landau levels filled, then F is an integer. Now, if you have such a system and it's a pure system, then you can argue that the Hall conductance parameter nu, which I defined before, is just equal to F. That's just a consequence of Lorentz invariance. Now, in the presence of impurities, you don't have Lorentz invariance anymore, but we said that the conductivity can't change if you vary things by a small amount. So even though now the filling fraction may not be exactly the same, nu remains constant. And the reservoir of localized states actually could be important, as I said, for being able to vary the fraction and get a plateau. Okay, what about the fractional quantized Hall effect? So this is much more complicated because if in that case, the filling fraction is going to be a fraction, so the Fermi level is not between 2 Landau levels, but inside a Landau level. And in the absence of electron-electron interactions, these states would be very degenerate. There certainly would not be a gap. So electron-electron interactions are essential to get a fractional quantized Hall effect, to get a gap, and they occur in a very non-trivial way. And after the discovery of the quantized Hall effect experimentally in 1982, it took almost a year for someone to come up with a wave function, an explanation. And the breakthrough was Laughlin's proposal, which explained, he introduced a trial wave function, which explained what was going on at filling fractions 1/3 and 1/5, 1 over non-denominator. And this wave function, it turned out it's the exact ground state in the limit of short-range repulsion between the electrons, but it turned out that it also had very good overlap with the ground state for when you have Coulomb interactions, as was shown by, as far as we could tell, by numerical calculations on finite systems. You have a sphere or a torus when you can go up to maybe 15, 60, 20 electrons maybe, and it agreed very well. So we understood that this was what was going on in that case. But there are many other fractions that have been seen that cannot be explained by Laughlin's wave functions. And the most powerful approach was introduced by Jane in 1987. It's called the composite fermion approach, and I'm not going to tell you about that in any detail, but it applies in particular to states of the form where nu, the filling fraction, is equal to p over 2m p plus 1, where m is an integer and p can be M is a positive integer, P can be the positive or negative. And examples are 2/5, 3/7, 4/9, 5/9. These are in fact precisely the states that you saw in the curve, in the experimental curve. These Jane states are the most prominent fractions observed in the lowest Landau level. They're not exact for short range interactions, but still they seem to agree very well with numerical calculations for finite systems. We don't really understand why it works so well, but it works very well. States in higher Landau levels are generally less well understood. Some of them are understood, some not. So there are many things open, but at the lowest Landau level, we kind of understand what's going on. Okay, so that's the background of or quick review of the quantized Hall effect. Let me turn to the subjects of my talk, to fractional charge and fractional statistics. Fractional. So the point is that the fractional quantized Hall states in all cases support quasi-particles which have fractional charge and have either fractional or non-abelian statistics. So fractional charge is easy to understand. It says that the elementary particles instead have a charge which is a fraction, a rational fraction of the electron charge, the fractional non-abelian statistics, that's more complicated. I will explain that later, but let me first talk about the fractional charge. Again, I should say that theoretical arguments for the existence of quasi-particles with fractional charge and and fractional statistics, which including the non-abelian statistics, are basically rigorous. So you can show them. I'll show it for fractional charge. They don't depend on any specific models of what the wave functions are or not. So we really know that if you see quantum Hall effect, fractional quantum Hall effect, these things are there. But to actually see them directly in experiments is much harder. I mean, there are indirect consequences which we can test, but the direct observations, especially if the fractional statistics are very hard, and it's only in the last couple of years that we've been able to see directly the fractional statistics. So let me turn to the case of fractional charge and give you an argument that's due to Laughlin, basically from the early 80s, and specifically at nu equals a third, why there must be, if you do have a quantized Hall state at nu equals a third, there must be fractional charged excitations. So what he said was, suppose we insert a solenoid of essentially 0 diameter at the origin in such a system. And if you have a solenoid with no current in it, it has 0 diameter, it basically doesn't scatter anything in 2 dimensions. It has no effect. Now let's turn on the current adiabatically, so the flux becomes equal to 1 flux quantum, which in units where I said h and e equal to 1, the flux quantum is just 1 over 2 pi. So when I've done that, as I'm turning it on, of course, I produce an EMF in the azimuthal direction by Faraday's law, and this azimuthal EMF is basically, if we look at 2 pi times the radius r times the electric field in the azimuthal direction, it's just equal to the d phi dt in these units. And this is going to produce a current in the radial direction, and that radial direction will be sigma xy times e phi. And in this units, the sigma xy is equal to 1/3. And so we get a current which is 1/3 e phi over 2 pi. If we integrate it over time, we see that it will have brought into the origin a charge of minus e over 3. So that charge is now there and it's stuck because sigma xx is 0. It can't go anywhere. So now we have a state which lasts forever, which has 1 extra flux at the origin, and it's physical and an extra charge of minus e over 3. But this state is really physically equivalent. The Hamiltonian is physically equivalent. The state is not equivalent, the Hamiltonian is physically equivalent to the original Hamiltonian, H naught. It differs only by a gauge transformation. So that says that the original Hamiltonian also must have had an eigenstate with charge plus or minus E over 3, which lasts forever. So those eigenstates must exist. Now, that's at nu equals 1/3. A more general situation is where nu is equal to P over Q, where let's say P and Q are in lowest, have no common denominator. So it's a fraction in lowest denominator. So then, of course, Laughlin's argument says, well, I turn on a flux, produce a charge E times P over Q. But I claim this is not the smallest possible charge, because if P and Q have no common denominator, divisor rather, you can always find integers such that n times q minus n prime p is equal to 1. And then if you take a combination of n and n prime positive quasiparticles, it will have charge q equal to E over little q. That is, we just take the electron charge and divide it by the denominator of the fraction. We don't care about the numerator. So there must exist such charges, but they're not necessarily the smallest charges. They could be the smallest charges. And indeed, in the Jane states, we believe, if the wave functions are correct, then these are the smallest charges that can exist. But we also know there's a theorem from Levin and Stern that if you have a quantum Hall state with even denominator q, then there must be quasiparticles with charge E over 2q. So in particular, there's a fraction, there's a charge there's an even denominator state at 5/2. And so that will have a charge not only E over 2, it will also have E over 4, because Q is 2. Okay, so now that's the theory. And I say that must be there, but how do you see them? So it took a while to figure out how to do this. It turns out that you can see fractional charges in several ways. The first way that was done is a little bit indirect, but it's not too indirect. It's something called shot noise experiments. To do a shot noise experiment, we take, let's say we take one of these ribbons of quantized Hall system, and we pinch it off, as I've shown here. You have a narrow constriction, which is so narrow that electrons or quasiparticles, whatever is existing on the edges here, can tunnel occasionally from one edge to the other. We want the tunneling rate to be small but non-zero. Now, if we put a voltage difference between the two edges, there'll be a net small current flowing through it, and there'll be noise, quantum noise. There'll be noise, fluctuating noise in the current, which you can measure, and that's called shot noise. And it turns out, it's been known for a long time, that under these conditions, you can back, if you can measure the shot noise produced as a function of the voltage, you can back out from it the charge of the particles that are tunneling across. Basically, it's proportional to the shot noise is proportional to this charge. And so from these measurements, I won't go through the theory in detail. It was first done by the Halperin group in Israel and Glassley group in France in '97. They saw charges E over 3 at nu equals 1/3, as you would expect. And later results from the Halperin group reported measurements of charge E over 3 at a whole bunch of filling fractions, including 5/3, 8/3. And E over 5, they found at nu equals 2/5. E over 7, they found at 3/7. E over 4, they found at 5/2. But there was a fly in the ointment. They found all this stuff, but then they found when they really lowered the temperature, things began to change. So, for example, at nu equals 2/5, as they lowered the temperature, at the lowest temperatures, instead of seeing E over 5, they saw 2E over 5. Or it was tending towards 2E over 5, and similarly at 3/7 and 2/3. So this said something funny was going on, and the explanation is, well, the quasiparticles that tunnel across are not necessarily the quasiparticles of smallest charge. And in particular, there were arguments using the renormalization group that at the lowest temperatures, let's say at nu equals 2/5, even though at higher temperatures, E over 5 might be the dominant thing, as you go to lower temperatures, the rate of tunneling for the 2 equals the 2E over 5 quasi-particle increases and may dominate what's going on at low temperatures. So that's a confusion, but it seems to be correct. Now, there's a more direct way of measuring what's going on. This was done more recently, which is using a charge sensing experiment. So these are basically experiments using a single electron transistor on a scanning tip to measure the charge sitting under the tip on a layer, and they can look for regions where there's a local puddle. We have impurities, and the impurities fluctuate, so you can actually get local groups of impurities which produce a small puddle of charge inside a quantized Hall state. And as I vary, say, the chemical potential, I can vary the potential or vary the magnetic field, but typically will vary the applied potential a little bit. Electrons or quasi-particles will enter or leave the puddle, because the puddle has some localized states at the Fermi surface. And you can actually measure the charge unambiguously, how much charge is going in and out. And these states are far from the boundary, so they're not complicated by things that are going on at the boundary. And we don't really care about which quasi-particles have the fastest tunneling rates, because you can do this on experiments that are very on scales of seconds, or the time scales that are very slow compared to the rate of tunneling of quasi-particles. So what you can measure unambiguously is the smallest quasi-particle charge that's thermodynamically allowed. You don't have to worry about these rates. And so that was done, whoops, wrong direction, by Martin in Ami Jacobi's group at Harvard. He measured, the first measurements measured indeed E over 3 at nu equals 1/3 and 2/3. These are difficult measurements, but they were carried out later, even in the higher Lambda levels, and they even measured these E over 4 quasi-particles at nu equals 5/2. So by seeing what happened when quasi-particles entered or lowered these puddles, they could directly measure the charge. And that's a direct confirmation of what we knew had to be there, but still was hard to see. Okay, let me I'm going to turn to fractional statistics, but before I do that, let me stop and ask if there's some urgent questions that people that have showed up that you think I should try to answer.
I think we are okay right now.
Okay, well, let me just take a drink of water here. Okay, so fractional statistics. So what the heck is fractional statistics? So there are actually a number of different ways of defining fractional statistics, and I won't go through all of them, but the way that I think is most useful for experiments anyway is to think in terms of what I call an effective wave function. So I could have a system which has let's say it's very close to nu equals 1/3. Let's say it may have a gazillion electrons in it, but a relatively small number of quasi-particles, of these 1/3 charged quasi-particles. And I'd like to be able to describe what's going on with these quasi-particles without having to keep track of all the electrons in the system. And since there's an energy gap separating the excited states from the in which it have more or fewer quasi-particles, I can look at a system with a fixed number of quasi-particles, and let me assume that the quasi-particles are not so localized that they're really frozen in place, but they can move around at least at some rate. And then I'd like to have an effective Hamiltonian, which would describe the rate of motion, their energies, solutions to the equation of motion, and so forth, that just refers to these quasi-particles alone. It should be just some function, and wave functions with some function of the positions of the quasi-particles. Now, there's a gauge freedom for choice of the phase of the effective wave function. So the phase of the effective wave function is not completely defined, but it's correlated with what Hamiltonian you're going to use for it. Now, it turns out then if I have fractional statistics, what that means is that if I want to use an effective Hamiltonian that contains only short-range forces, I am forced to use multi-valued wave functions. And that specifically, if I want to do that, then what happens is if I interchange, the wave function must be such that if I interchange two quasi-particles around some path, let's say a counterclockwise path that doesn't include any other, enclose any others, then what will happen is the wave function must be multiplied by a phase factor. It's basically coming back to the same state, I'm assuming. And that phase factor, let's call it e to the I theta. And for a boson, of course, that would be just 1. If it was a fermion, it would be -1. But for fractional particles, it's neither. It's something in between 1 and -1. And we also know that if I move one quasi-particle all the way around another, that's topologically equivalent to interchanging the quasi-particles twice, because I'm moving it around 360 degrees rather than 180 degrees. In that case, it's going to pick up a phase e to the 2I theta. So if e to the I theta is not plus or minus 1, e to the 2I theta is not 1. So that means I don't come back to the same state. I don't come back to the same phase factor that I had before. The amplitude can be the same, but I have to pick up an extra phase factor. So I have to have multiple valued wave functions that differ by different phase factors. Now that's a little unpleasant. You can define your quantum mechanics to work that way, but you could also say, I want to work with single valued effective wave functions, either bosons or fermions, let's say bosons. And I can do that by making a gauge transformation. But if I do that, it means that the Hamiltonian will now have to include effectively long distance interactions by a gauge field. That gauge field it's called a Chern-Simons gauge field. And what it's equivalent to is attaching a quantum of magnetic flux, which we'll call the Chern-Simons flux, to each particle, and the value of the flux in units of the flux quantum will be this angle theta over pi. So if theta is for bosons, that would be 0. Fermions, that would be just 1, would be 1 flux quantum, but otherwise it's some fractional number of flux quanta, and that is completely equivalent to having a multi-valued wave function. Okay, and then I should say just a history to the idea that you could have things other than bosons and fermions in 2 dimensions dates back at least to Linus and Merriam in 1977. This was amplified a lot by this idea by Frank Wilczek, who introduced the idea of anyons to describe these things which could have any statistics other than fermions and bosons. And the fact then there was a paper by myself in 1984 and another one by Aravis, Triefer, and Wilczek in 84, which showed that not only were these things possible, but that they really should occur in fractional quantized Hall states. So this was, I think, the first demonstration that fractional statistics really does exist, or should exist, in the real world. And that made us, that we were excited about that. Okay, I also mentioned non-abelian statistics. What are those? So the systems I was talking about assume that if I specify the positions of the quasi-particles, I have a well-defined ground state, except for some phase factor. But in certain systems, you could have a situation where where the ground state's actually highly degenerate. In particular, non-abelian statistics occurs in a system where if I have n well-separated quasi-particles, the ground state is actually extremely degenerate. The degeneracy grows exponentially with the size with n. Now the degeneracy, it's not actually a perfect degeneracy, but the degeneracy, the difference between the energy levels in this manifold or the Hilbert space of ground states falls off exponentially with separation. So it can be made extremely small, at least in principle, and it's often neglected. But in practice, of course, you have to keep track of it. And what happens in that case is if I interchange two identical quasi-particles, I get a unitary transformation of some kind within this Hilbert space. I'm still in the ground state Hilbert space, but it's not necessarily the same state I started with. And if I interchange them in different orders, I may wind up with different final unitary transformations. So that means that these group of transformations are they don't commute, and so we call it non-abelian. But it also turns out that you can argue in these cases that although the unitary transformation may depend on the order in which you've wound things around each other, it doesn't depend on other details. It's just determined by topology of the braiding of the world lines, the way you braid them around each other. And we say that this unitary transformation is a representation of the braid group, and that gives you limitations on the number of the kinds of different non-abelian statistics that could, in principle, be seen. And I'll return to that shortly. But let me now turn to the question: how would you see? Let's go back to ordinary so-called fractional statistics, and how would you see them? How would you try to see this? And the obvious way of trying to see it is with an interferometer experiment. And this shows sort of an ideal interferometer experiment that you might think about in the case of just a nu equals a third, and we're trying to look for the fractional statistics of these E of a third quasi-particles. So to build it, this is a Fabry-Perot type interferometer for quantum Hall effect. So I have a Hall bar now with two notches in it, two narrow constrictions, and I assume that these are narrow enough so I get a small amount of tunneling across each of these constrictions with some tunneling amplitude T1 and T2. And in the absence of constrictions, of course, I would have only there's no transport in the middle here, but current could go along the edges if I inject a current along one edge. So I get quasi-particles that travel along the edge, and they can travel in the other direction, the other edges. And if there's a net current, there's a difference in the number of quasi-particles on one edge versus the other. And there can be tunneling from one edge to the other. And if there's no tunneling, then this is a constant voltage, and there'll be no voltage difference between these 2 points. If there's tunneling, then I get some backscattering there'll be a drop in the voltage, which I can measure, and I can figure out how much current has tunneled between the two edges. And of course, that would be proportional to if there was no interference between these two edges, I would just take the square of the tunneling amplitude here and the square of the tunneling amplitude there, and that would be the amplitude, the magnitude of the tunneling. But if there's interference, then I have another term, which will be proportional to T1, T2 star times some phase factor, and the phase factor is going to depend on what's happening inside this interferometer here. What happens if it's the amount of phase I'd pick up if I have a particle going all the way around this loop. And that will certainly depend on the magnetic field enclosed, obviously. And so I can see oscillations it'll depend on the area also, the amount of flux inside. So if I can vary the magnetic field, I would see oscillations in the backscattering voltage. I vary if I put a side gate here, I can vary the area and see these oscillations, and I can measure their period, and that would give me some idea of the charge of the particle that's tunneling around here. But in addition, I can consider what happens if I have not just an empty space here, but I have some number of localized quasi-particles. Here I've shown two quasi-particles of charge a third, or there could be one or three. Now, if the quasi-particles have a fractional, if there's fractional statistics, so I have a fractional flux quantum of Chern-Simons flux attached to it, it's going to give me an additional phase. So I'd get a phase shift depending on whether I had a quasi-particle here or not, or how many quasi-particles. And I could hope to try to see the phase shift as I add or subtract one of these quasi-particles. That's the idea. And it's very simple to say, but very difficult in practice, I should say. And it's only last year that this was successfully seen in the 2/3 state by Nakamura and people at Purdue. And this is a picture of what they saw. So here's magnetic field varying over a small range where I'm sitting in around nu equals 1/3. And this is a gate voltage, which is changing the area of the interferometer. And you see in these regions, you see these stripes. So as I vary the magnetic field, for example, I get red means that, let's say there's a maximum in the conductance, blue a dip. And so you get oscillations in the conduction, maximum, minimum, maximum. And the spacing between here is the spacing that I would get to add one flux quantum for a particle of charge E over 3. So it's actually 3 times the spacing that I would get if these were integers. And similarly, this is a spacing for adding particles in this direction. So let's just look at this. So we see these things, they're spaced by a distance of a certain distance apart. And what happens here is you can see a glitch where there's a jump in the phase, and we associate this with actually a quasi-particle leaving, so that there's a jump of minus because it's leaving this, the jump in phase here that we measure relative to this being 2 pi, this is 2 pi over 3 minus 2 pi over 3, roughly, not quite exactly, but pretty close. And we interpret that as being the phase that happened when a quasi-particle leaves. And here's another jump and another jump and another jump. And you could say, okay, well, this looks very simple. Why was it so hard to have this happen? Well, the reason is that it's very hard to make a sample where in this regime. It's usually very difficult to control the number of quasi-particles inside the interferometer area. Most experiments have been done with an interferometer in a compressible regime where EF is in a region of localized states, so it's not a true energy gap. And then what happens is that quasi-particles are entering and leaving all the time. It's very hard to see an individual jump. In fact, you can't control it. And also, not only that, quasi-particles can affect the edge states not only through their statistical phase, but also by their Coulomb interactions. It can change the phase by changing the size of the area, basically, and that can complicate the interpretation of the interferometer's phase. So Nakamura had to work very hard to construct a sample where Coulomb interaction is very well screened, so it's not messing things up, and all the other properties are very well controlled. And then they had to be able to make it small enough so the energy gap was big enough, and they could get the Fermi level inside this energy gap, and there have to be a very small density of impurity states in the energy gap. If you get outside the energy gap, then there are a lot of impurity states, and you can't see anything. So that's why it was so difficult to see. Let me say something very briefly about the search for non-abelian statistics. There are many kinds of non-abelian statistics, but the simplest kind is called Ising statistics. In that case, the ground state of n quasi-particles has a dimension 2 to the n over 2, and such quasi-particles are called Ising anyons, and it's been proposed that the fractional quantized Hall state at nu equals 5/2 has quasi-particles with charge E over 4, which are Ising anyons. So that's a case where you could look for the Ising anyons. I saw that somebody had a hand up. Was there a question that someone wants to ask?
Yes.
Rishi, do you see the person with the hand up?
Yeah, I have allowed Yogesh to talk. Yogesh, you want to ask a question? You are muted. You have to unmute yourself.
Yogesh, if you are having technical difficulties, maybe we can save your question to the end and let Bert continue then.
Okay, let me go on and just say, so how would you try to see these Ising anyons? So again, we could try to do interferometry. Now, it turns out if you have Ising anyons, or any, actually, this would be true for any non-abelian case, the period of the interference as well as its phase depends on the number of anyons inside the interferometer. For example, for Ising anyons, if there's an odd number of E over 4 quasi-particles at nu equals 5/2 in the interior, then if you bring another E over 4 quasi-particle around the outside of the interferometer, as it goes around, it will actually change. Because it's not abelian, it will actually give a unitary transformation that actually changes the quantum state. It doesn't just multiply it by a phase factor. So that means if I have a quasi-particle tunneling at at constriction 1, it will not interfere with a quasi-particle that tunnels at the second constriction, because the wave functions for a particle going around, they differ by not just a phase factor, but they're actually completely orthogonal. And then you would say, okay, so then the interference associated with an E/4 particles, when I have E/4 in the middle, will be absent. On the other hand, if there's an even number of E/4 particles in the middle, then going around the outside doesn't change it. So then you would see an interference corresponding to that period. So that's what's been looked for. It's kind of an even-odd effect in the interferometry, depending whether there's an even or odd number of particles, of quasi-particles in. And there have been experiments by Willett and collaborators over a period of years, which do show evidence for E/4 alternation in the interference period, depending on the number of E/4 quasi-particles inside the interferometer at nu equals 5/2, also at nu equals 7/2. But the evidence is statistical. It's a little hard to be sure about it. And there are other explanations that have been observed that could be put forth for these observations. So I would have to say it's maybe direct, but it's not conclusive. At least it's certainly controversial at this point. So I would have to say that we haven't seen it, but it definitely, but maybe we've seen it. But I should say that there actually, at this point, and recently, there have been some really substantial questions about what is actually going on at the fractional quantized Hall state at 5/2. So this was discovered back in 1987, and Moore and Reed in 1991 proposed a ground state, which is known as the Pfaffian state, which would support these Ising anyons that I've talked about, with charge E/4. And later it was pointed out, about 10 years later, well, actually 2011, actually 20 years later, it was noted that actually the particle hole conjugate state of the which we call the anti-Pfaffian, which has a very similar energy, it's almost identical energy, and identical anion properties, also Ising anyons, is actually topologically distinct from the Pfaffian state. And in principle, these states can be distinguished by their thermal conductance. So they're not identical, and they're not, you have to destroy an energy gap to go between them. And numerical results on small systems slightly favor the anti-Pfaffian for realistic Hamiltonians, but we would be not terribly upset if it turned out that the Pfaffian was really the case. And so, okay, so what is this, the quantized thermal conductance? So what's going on here? Why is there a thermal conductance? So because a quantized Hall state is gapped in the bulk, heat can only, ideally at low temperatures, can only be transmitted along the edges. And it turns out that it's a one-dimensional system then that conducts heat. In general, you can write the thermal conductivity as being some dimensionless number K times kappa naught times T, where T is the temperature, and kappa naught is some combination of fundamental constants. And it turns out that K is, in a quantized Hall state, K is topologically protected, just like the ordinary conductivity, in this case, due to energy conservation rather than charge conservation. So K is a constant within a given state, and for integer states, K is just equal to the number of, it's an integer, just the number of states that's filled at each edge, which is also the Hall conductance. In a fractional quantized Hall state, you can actually, in some cases, have edge modes that move sometimes in different directions. In that case, ideally, this K should be the difference, the absolute value of the difference in the number of left movers and right movers. But in any case, if you have abelian quantized Hall states, K should be an integer. On the other hand, because the states that they carry just integer conductance, but non-abelian states can have a fractional value. In particular, non-abelian states with Ising anyons have what we call Majorana edge modes, in addition to the normal edge modes. And Majorana edge modes, they have no charge, but they do carry energy. They have only 1/4 the thermal conductance of normal edge modes. So states with Majorana edge modes can have a half integer conductance. And the Pfaffian and anti-Pfaffian states have different numbers of Majorana edge modes, so that one predicts that the Pfaffian should have K equals 7/2 thermal conduction, and anti-Pfaffian is K equals 3/2. So you'd like to be able to measure that and see the difference. Now, it turns out that measurement is very difficult. Measurements of thermal conductance have only in quantum Hall states have only been done recently. Integer states were done in 2013 by Jesuanis, et cetera, in France. And in 2017, Banerjee et al. And Heidelberg's group did it for the fractions. What they found originally were measurements at 1/3, 2/3, 2/5, 3/5, and 1 and 2. They all agreed with the predictions. Very nice, on the lowest Landau level. Much more difficult were experiments in the second Landau level, which they only did in 2018. At nu equals 7/3 and 1/3, at 8/3, they found more or less what they expected. And then they looked at nu equals 5/2, trying to see whether it would be 7/2 or 3/2. And what they found was neither. It was really shocking. This is really shocking. They found K equals 5/2, not 7/2 for a Pfaffian, not 3/2 for an anti-Pfaffian. And what is going on is very confusing. Now, it's true that a particle hole symmetric state, which had precisely K equals 5/2, had been proposed by Danson some years earlier, called the pH Pfaffian, particle hole symmetric Pfaffian, as a mathematical possibility, and closely related states have been proposed in earlier contexts. And the pH Pfaffian, if it exists, would have Ising anyons. It would be very similar to the Pfaffian and anti-Pfaffian in that respect, but it would have a different thermal conductivity. So maybe that's what's going on. But numerical calculations have strongly disfavored the existence of such a state. They've never shown anything like it in a finite system with realistic parameters. So we really don't know what's going on. It's possible that we're really just mistaken and the pH Pfaffian is really the ground state after all. Zucker and Feldman in 2016 pointed out already that certain earlier experiments were better agreement with predictions of the pH Pfaffian than either the ordinary Pfaffian or anti-Pfaffian. And they proposed that maybe somehow the pH Pfaffian might be stabilized by disorder that can't be really taken into account. Theoretically, this is possible, but no calculation that I'm aware of trying to understand effects of disorder really supports this as being a likely explanation. So this is really a mystery, and it's one of the big mysteries that is connected with fractional statistics vaguely, and that has to do with quantum Hall systems. So I think that wraps up the body of my talk. I would just like to make a few concluding remarks. I've just been talking about one aspect of quantum Hall systems, namely the fractional statistics, but there's a lot going on. There are a lot of open problems in quantum Hall systems today, even though it's been around for almost 40 years. In addition to the five-halves puzzle, there are a number of outstanding experiments, even on integer quantum Hall systems, that are very poorly understood and very confusing. There are a number of fundamental theoretical questions which remain open. I'll mention a couple of them. And I should also say that in terms of fractional statistics, it's been proposed that we know that in principle, for some weird Hamiltonians, non-abelian states more complicated than simple Ising anyons could exist and would be very interesting. It's been proposed that they may actually occur at some known filling fractions like 12/5, but it's very far from clear whether this is correct or not. So this is a very open question. And there might be other ways of constructing it in inhomogeneous systems and so forth. There are many open practical questions. So at this point, given a microscopic Hamiltonian of some kind, can you predict what types of fractional quantum Hall states will occur at different magnetic fields? Well, we can in the simplest case, but not in more complicated cases. And then more generally, if you have if we construct some kind of system, what is the correct Hamiltonian? What about mesoscopic systems, which are small, so that they're not infinite, but very, and what happens not at zero temperature, but at finite temperatures? What happens when you apply not a small voltage, but a relatively large voltage? And these are understood to some extent, but there are many open questions. and certainly a lot of quantitative questions that are not understood. And indeed, if you discover a new system, you can ask, what's the correct microscopic model that applies to it? And new systems include new materials. A number of new materials like zinc oxide recently has been developed where they've seen fractional quantum states. There are multi-component systems like systems of two parallel graphene sheets where you see new fractions. And as I mentioned, we understand relatively well what goes on in the lowest Lambda level. Typically, if you go up to higher Lambda levels, it's much less well understood. We see some fractions in higher Lambda levels. We see various other things like Wigner crystals and so forth. And exactly what's going on and in different materials is an open question. Open fundamental questions. Again, I just mentioned a few of them. There's a lot of debate about what is the mathematical nature of the transition between different quantum Hall states in the presence of disorder, even in integer case. What's the nature of the transition between nu equals 1 and nu equals 2, or nu equals 1 and nu equals 0, even between the insulator and the quantized Hall state? And there are experiments that don't, and then numerical calculations that don't exactly agree, and there are theories that don't agree with either. So we're trying to figure out what's going on. As far as I know, I believe there is a complete topological classification of abelian quantized Hall states. As far as I know, it's not true for non-abelian states. The question of exactly what happens at nu equals 1/2, which is this unquantized quantum Hall effect that Kedar mentioned, where you don't see a quantized Hall plateau. There are a lot of interesting things you do see. I think we understand the experiments reasonably well there, but there are some open theoretical questions, particularly about particle Hall symmetry, which remain open. So there are certainly theoretical questions. And let me finally just mention some references if you want to follow more. There's a whole, we have a whole book, an edited book that I edited with Janandra Jain called Fractional Quantum Hall Effects, New Developments, edited by us and published by World Scientific in 2020. And more recently, a review article specifically on fractional charge and fractional statistics in quantum Hall effects with Dima Feldman, which is come out in reports on progress in physics. Let's say, I guess I don't have the exact reference. It's also available on the internet. Okay, with that, let me stop. Thank you and ask for questions.
Thank you. Rajdeep, will you conduct the question answer session?
Okay. Yeah. Thanks. I will ask everybody to just raise their hands, and if you have a question. I have some questions in the chat. Let me start with them, and then I'll go to the other people, both in the panelists and in the attendees section. So the first question is from Sachiraj Mishra, and he asks, can quantum Hall effect occur in 1D or 3D material? Since as far as his experience goes, he has only seen this in 2D. And if it happens in 1 or 3 dimensions, will we observe some different type of quantum Hall effect phenomena than with the 2D material?
Yeah, so I don't think it can happen in 1 dimension. I'm not sure what would be the equivalent of a Hall conductance. There are, of course, topological states in 1 dimension, but not quantum Hall states, that, as far as I know. 3 dimensions, well, yes and no. What we predict and what we expect is that there can be 3-dimensional systems which basically either spontaneously or because of the way they're constructed wind up being a bunch of layers. You can think of having a 3-dimensional system which was 100 layers of quantum quantum Hall state, and then of course it would have a zero conductance in the x and y directions and zero longitudinal conductance, but it would have a Hall conductance which would be 100 times the conductance would be 100 times e squared over h. It would have a conductivity which would be quantized, and this has so it's been seen in some artificial structures up to, I think, with gallium arsenide, up to a structure which went up to, I think, 50 layers, where electrons could tunnel between the layers without a magnetic field, but once you put a strong quantizing magnetic field on, the conduction dropped to 0 in the perpendicular direction, and it became something like the top and bottom layer weren't working, and you got something like 48 E squared over H. And recently there have been some reports, and it was predicted that you could have a situation where it would be basically isotropic in the bulk, but it would spontaneously form layers in a magnetic field. And this there's indications that's been seen in zinc telluride in certain materials, but not zirconium telluride. So there's some indications, but it's basically a stack of two-dimensional layers, and there's no true three-dimensional version.
Thank you, Bert. I see Shiraz has a question. Shiraz, will you just unmute and ask?
Hi, Bert. Thanks for the fantastic talk. I wanted to ask, is there ever a situation in which you have a gas of these fractional statistics quasi-particles, a weakly interacting gas? And if so, is the dynamics of such a gas understood?
Yeah, so what do we mean by a gas? So let's start at nu equals a third, right? So if the density is slightly larger than nu equals a third, you have a small number of these 1/3 quasi-particles, which would, if they're impurities, they're going to freeze out at low temperature into the impurities. If there were no impurities, we believe they would form a Wigner crystal. You'd have a crystal of these things, and the crystal would be localized. If you had any kind of impurity at all, they would get localized and they wouldn't conduct. Now, suppose we have no impurities and we increase the density. We let's say we decrease the magnetic field, or we increase the density of electrons, so we get more and more of these quasi-particles. What we believe would happen is you'd get a certain density and the Wigner crystal would melt. And then you'd say, okay, we now have a liquid, a quantum liquid of these nu equals a third quasi-particles. I think that's what you're really talking about. Now, what happens there? Well, what we believe will happen is that, we know that if we have enough of them, what will happen is these quasi-particles will form something like a Laughlin state, taking into account the fractional statistics, and they will themselves form basically a new quantum Hall state at say 2/5. And indeed, that's what caused me to think about the fractional statistics in the first place, because it turns out that if you take a liquid, a quantum Hall liquid of these fractional charges at nu equals a third with the right density to bring you up to filling fraction 2/5, and if you assume they have this 1/3 fractional statistics, and you make a Laughlin state out of it, you'll open up an energy gap, which will be, and you'll get precisely an explanation. This would be the explanation for the nu equals. This is one possible explanation for the nu equals 5-halves state. In other words, it is a quantum Hall liquid of these quasi-particles, and you could also get other fractions that way. Now, this is not numerically the best way of understanding the 2/5 state, but it's, I think, one way of understanding what would happen if you have a quantum liquid of these fractional charged particles in a magnetic field.
Thank you.
Okay, there's thanks, Shiraz, thanks, Bert. There's one question from Alok Ray, and he's asking, is there a Wiedemann-Franz law for nu equal to 5-half states? And if yes, how does it differ from standard fermions like electrons in a conduction band?
Okay, so this is very interesting. So the answer is no, but so at 5-halves, if you're really in the ground state, there's an energy gap, and so everything is frozen out. And so it's hard to, it's not very well defined. If you add quasi-particles, then if they can move thermally, then it gets more complicated, and I think it depends on on details of what the interactions are and so forth. You can ask what happens at nu equals 1/2, where the quasi-particles are not frozen out, and there we think that there are deviations from Wiedemann-Franz, and certainly we would expect deviations from Wiedemann-Franz in if you well, it's never been done experimentally, but we would expect that at say at nu equals 1/3 or something, if you had 1/3 quasi-particles and you heated enough, so there were enough of them so they were mobile, we would not expect simple Wiedemann-Franz. But these are actually somewhat open questions.
Okay. I see Shubhro has raised his hand. Shubhro, will you unmute and ask?
Yeah. Hi. Thanks for the nice talk. Would you go back to this experimental data from the Purdue University about the fractional statistics, please?
Okay, let's see.
Yeah.
Oops. This slide, you mean?
Yes. Yes. So maybe you discussed this, but why are these jumps in phase occurring at that regular interval with that regularity along the straight line?
So no, they didn't. Oh, okay. So what's happening here? So first of all, what we believe is that the gap is not completely clean. There are some impurity states, localized states, and what happens? Each of these jumps is a jump where some impurity state empties out. And you can see if I look horizontally, they're not equally spaced. They're somewhat randomly spaced, but they do occur on a, if I look how they go when I vary the magnetic field and the gap.
They seem to lie on a straight line.
Yeah, they seem to lie on a straight line. And what we think is happening here is basically, if you vary the magnetic field, it slightly varies the Fermi level.
Mm-hmm.
And it does that because, well, basically there's a cyclotron energy which is going up as you increase the magnetic field. So it sort of pushes all the energies up, but it doesn't necessarily push the localized states up by the same amount. So there's so if I just vary the magnetic field, let's say just go horizontally. As I go horizontally, it comes to a point where one of these impurities comes through the Fermi surface and empties out, and then another one does. Now, if I vary the gate voltage, that also shifts the impurities, and it basically shifts the impurities. It causes the same, but it shifts the potential relative to the chemical potential, and there's a certain ratio of the shift due to applying a gate voltage relative to applying a magnetic field. It seems to be more or less a constant, and so it's simple models would give you something where these things would occur on straight lines. That is, the shift due to magnetic field is just proportional to the shift due to applying gate voltage.
Okay.
But spacing between them is somewhat random. And I should say, again, it's important to point out, if I vary the magnetic field too much, I start getting into the regime where I start occupying a lot of these. And then you no longer see then it goes over into this, so what I call the compressible regime, and you can't see these stripes anymore. You can only see these stripes over a very narrow range of magnetic field where the Fermi level stays inside this energy gap. The energy gap is pretty small, so you have to be very careful.
Okay, so there's one question I'll take up from the question and answer part. It's from someone who is anonymous. Says the interference or tunneling effect naively feels to be a single particle effect, while fractional quasi-particles or statistics result from many body effects. Does this mean we can think of or treat fractional quasi-particles or statistics using a effective single particle picture?
Yes. So what we believe. So that's exactly what I was claiming. I guess what we believe is that if you have a small number of these fractionally charged quasi-particles, you can describe them by an effective Hamiltonian, which looks a lot like an ordinary Hamiltonian. It has a magnetic field in it. It has the charge of the quasi-particles in it, but in addition, it has to have this extra, if I want to treat them as, say, bosons, I have to, or fermions, I have to add, in addition to the usual terms, I have to add this extra Chern-Simons interaction with the Chern-Simons gauge field. And once I do that, then the statement is I should be able to treat them as ordinary quasi-particles. Now, it's a little, that's if I have two quasi-particles in the bulk. Here, I actually have one quasi-particle in the bulk, and another one is going around the edge. So the edge is a little more complicated because there I have a whole metal, and the quasi-particle that's going around the edge is interacting with many other quasi-particles that are also on the edge. The one that's tunneling is the one I'm keeping track of. There are others that are in the background, and they should be taken into account by something like a Luttinger liquid theory. So it's a simple Hamiltonian isn't quite right, but still you can treat them very much like ordinary particles.
Okay. There's a question from Sharmishta Shahu, who asks, what about the theory that considers puddles of Pfaffian and anti-Pfaffian states to construct a particle-hole symmetric state for nu equals 5-half? How can one experimentally verify such a picture? That's the picture.
Well, okay, so that's one of the things we looked at, and it's possible in principle. I'm not sure how to distinguish. Well, so we could talk about how to distinguish it. It turned out that it looked like in order to get into this state, you had to adjust parameters very carefully, that it was not a very stable state. It seemed very unlikely that this is what was going on. There were arguments by Steve Simon and co-workers who looked at who did actually try to calculate the energies of the Pfaffian and anti-Pfaffian, and they claim that the energies are so different that it's really very unlikely that you could get puddles of coexisting puddles of the two of them within the range of magnetic fields where they actually see the 5-half state. So these are all sort of numerical calculations that make it seem unlikely. If there really were puddles, I don't know whether there'd be a way. So we would have to be very clever to try to somehow back that out. Presumably the puddles would have to be very small and very finely interchanged. Otherwise, you would find that the Hall conductance would be very random. But this is a very good question of how, if it were true, how would you be able to show it were true? Well, okay, that's one of the open questions.
Okay. So there's another question from Saurav Srivastav now, who asks, is the presence of localized states necessary for the description of the fractional statistics of these fractional states? It seems to me that for experimental observation in interference experiment, this is the case, but is it necessary to describe in a theoretical description, put in localized states and disorder?
Well, okay, so I think you need to have what I call localized states, and we'll have to make precise what we mean by that a little bit. They could be caused by disorder. They could be, in principle, caused by some kind of Wigner crystallization of these 1/3 quasi-particles, but they have to be somehow trapped and frozen out. Otherwise, you wouldn't get a Hall plateau. In other words, if the nu equals 1/3 quasi-particles were completely free to move, then what would happen is if you vary the magnetic field even very slightly from nu equals 1/3, then if I applied an electric field, these extra quasiparticles would contribute to the Hall conductance, and you wouldn't get the quantized Hall conductance anymore. In fact, if it was really if there were no impurities at all, then I would have essentially a Lorentz invariant system, and I would just find that the Hall conductance would just be given by the ratio of the density to the number of magnetic flux quanta, just as it would be classically. So I have to have some means of freezing out these extra carriers and freezing them out. They don't have to be frozen forever, but they have to at least be frozen out to the extent that their contribution in the presence of an electric field is negligible.
Okay. Shaurav Manna asks, in a recent proposal, it was shown that the combination of thermal Hall conductance and short noise in the partially coherent regime can be used to single out the candidate state for Five-halves case. What about experimental implementation of this? Are there difficulties and are there prospects?
Could you say it? Could you say once more the combination of thermal Hall and shot noise?
And short noise, yeah.
Yeah. So, well, they're not usually done in the same apparatus, but I don't see. So I think the shot noise has been done, and it seems to show E/4. I don't see that there's much problem there. The thermal conductance, I think it's an independent experiment, and it does show this, at least approximately, the 5-halves. Now, there could be problems with, so one of the problems with the experiment is that I oversimplified a little bit, but the thermal conductance is quantized in the limit of a long system where you get, where there's adequate, if you have many modes traveling in different directions, the thermal conductance you measure won't be the thermal quantized Hall, the quantized Hall value until the edge is long enough so that you get scattering between the two edges, between the various edges, and so that they've equilibrated. So there's some arguments about whether or not the measurements are done over large enough samples, large enough distances, so that that some kind of that true equilibration has taken place. And indeed, the value they get out does vary slightly. It's not exactly 5-halves. It can be it varies with temperature and so forth. So there certainly could be experimental problems. There are a number of different experiments that have been done now, even with, let's say, where you have a boundary between nu=3 and nu=5-halves rather than the vacuum. And they all seem to support, these conduction experiments seem to support this pH 5-halves thermal conductance. But there certainly could be problems with the experiments, and better experiments might be useful. As for simultaneously measuring shot noise and thermal conduction, I'm not sure what that adds to measuring them separately.
Okay, so we have been having a lot of question and answers. So I'll take one last question up, and then we will try to close the session. This is from Dipan Betal, and he asks, what effects does having an environment or noise have on the non-abelian phase and the corresponding statistics?
So say it again, what effect does noise, what was the first one?
Yeah, so if you have non-abelian phase or corresponding statistics,
yes.
What is the effect if this is coupled to a bath or an environment or noise?
Okay, well, so of course, if the any kind of noise is going to weaken your, will tend to weaken the interference signal. As you raise temperature, interference signals decrease rapidly with temperature because you are getting fluctuations in the number of quasi-particles on the edge, the energy. So in a Fabry-Perot interferometer, the phase is depends on the phase difference between the two paths depends on the energy of the electron or quasi-particle. So if you have thermal fluctuations, that gives you a fluctuation in the phase, and that will tend to wipe out the signal rapidly. If you put external noise on, that will also presumably wipe out the signal, and that would certainly be the same in the non-abelian case. In addition, noise could change the number of quasi-particles. That could be another factor. So certainly you want to get rid of as much noise as you can and work at temperatures as low as you can.
Okay, so thanks for answering a very large number of questions, and I will hand it back to Kedar, I guess, or Shiraz. Kedar, you want to take over, or Shiraz should take over?
Well, I think it only remains to thank Bert for a really fantastic talk. We really appreciate that he made time for this. And we hope that we continue to have talks like this at this level. Shiraz, anything more?
No, just thanks from me again, Bert. Also, if it's okay with you, if you could send us the slides for your talk, we'd add that to our, we did put them up on our website so people can go back and look at your slides, if that's okay with you.
That's fine. I'm happy to do that. And again, I thank you very much for a very stimulating audience. I think the questions were fantastic, and I hope that I went on. I didn't go on too long, but anyway, it was a pleasure.
The talk was perfect. It was perfectly timed. Everything was great. Thank you so much.
Thank you, Bert.
Okay. Thank you again.
Okay.